Just finished discussing translations. Let me just make one comment. Time translations were exponential of minus IHT over h bar. Space translations were the exponential of plus IAP over h bar. So there's a sign difference in the exponential. I just want to stress that that sign difference in the exponential is rather easy to understand. Remember, the Schrodinger equation tells us that IH bar d by dt on psi is equal to h psi, but we know that the momentum operator acting on the wave function is minus IH bar d by dx. So there's a sign change in the operator going from the Hamiltonian, which is a plus IH bar d by dt, to the momentum, which is a minus IH bar d by dx. And that's why that sign difference in the exponential should look pretty natural to you. Okay, so we've discussed translations. So the natural thing to discuss now is Lorentz transformations. So how does our field behave under Lorentz transformations? Okay, well, let's imagine that we have some space-time diagram. We have the t-axis, the x-axis, and there's a point over here, a point P, okay? And let's say that point P has coordinates x mu. Then under a Lorentz transformation, x mu goes into lambda mu x nu, or you can write this as lambda x mu. So I'm imagining that we call P x mu before the Lorentz transformation, and we call P lambda x mu after the Lorentz transformation. So I'm assuming that we're doing a passive transformation here. So what the Lorentz transformation does, it changes how we label points. If the point was labeled x mu before the Lorentz transformation, it's labeled lambda x mu after the Lorentz transformation. The field was called phi before the Lorentz transformation, and it's called phi prime after the Lorentz transformation. Okay. When we say we've got a scalar field, what the scalar refers to, we don't want this field's value to change in space-time. We want it to be invariant under a Lorentz transformation. So that means the field evaluated at point P before the Lorentz transformation must be equal to the field evaluated at point P after the Lorentz transformation. Now, take into account what we call the point P. We want phi of x to be equal to phi prime evaluated at lambda x. So this is the definition of what we mean by a scalar field. Now let's introduce a new coordinate. So let's introduce some coordinate y mu. And how is y mu defined? Well, x mu is given by lambda to the minus 1 mu y mu, or equivalently y mu you can think about as lambda mu of x mu. Okay, and in terms of the coordinate y, well, we would have phi. Now x is lambda inverse y is equal to phi prime, and lambda x is just y. So this is another way that we can write our transformation law. Finally, how do we actually do a transformation? Well, phi prime of y, this would be do the Lorentz transformation. And we know how to transform operators. So as usual, there will be some unitary operator u of lambda which performs the Lorentz transformation, and phi prime of y will be u of lambda, phi of y, u of lambda. And this we want to be equal to phi of lambda inverse y. So that's how we want our field to transform under a Lorentz transformation. So let's just capture that as another axiom. Good. Let me just clean a little bit of space here. We don't need this anymore. That's perfect. Good. So let's say axiom 4. This is that u dagger of lambda phi of x u of lambda is equal to phi of lambda minus 1 of x. Okay, I've just changed the name x to y. That's no problem to do that. Now, let's just pay attention to one thing. So these first two axioms over here, the fact that space-like separated fields commute, and the fact that the field is Hermitian, this must be true for any field that we choose to consider. Next, these two axioms over here, which tell us how the field behaves under translations, that's axiom 3, and under Lorentz transformations, that's axiom 4, this must be true for a scalar field. So the one thing that we haven't put into our analysis yet is how do we put in the fact that the field is free? We expect that to simplify our description. So let's turn to that now. We're going to write down one more axiom, and that's going to be the axiom which tells us what it means to have a free field. Now, remember our logic. We said a free field means that the spectrum, the energy spectrum, is additive, okay? And because the energy spectrum is additive, it means we should build our field out of harmonic oscillator creation and annihilation operators. Good. Okay. So how are we going to do that? Well, let's just assume a general linear combination. So what do I mean by that? Well, let's take our field phi of x to be equal to, we'll have an integral d3k, our oscillators are labeled by momenta. Then we will have the most general coefficient we can think of. So something that depends on position and momentum as an arbitrary function. We've got ak plus, and then we'll have a coefficient g, again, an arbitrary function of position and momentum, and a dagger of k. Okay, so that's what we're going to assume for our field. We have to say what these oscillators are. Well, these are the normal annihilation and creation operators of the harmonic oscillator. And the way that we specify them, by now this should be familiar to you, we write down some commutation relations. So the commutator between A and A dagger is a Dirac delta. And then the other commutators that we have is that AK must commute with AP, and the same thing for the daggered operators. Okay, good. This is what we want to write. Now, this is not great as it's written. The reason for that is that if we look at this expansion of the field, well, this integration measure is not Lorentz invariant. And because this delta function, that Dirac delta of k minus p, is not Lorentz invariant, it means the oscillators are also not Lorentz invariant. So this linear expansion that we've written of our field, every single different inertial observer would write a different expansion. So let's try to fix that. So the first thing that we're going to do is we're going to say, well, let's write phi of x as an integral of d3k over 2 pi cubed. That's just a constant. Again, I'm putting that in so that our Feynman rules come out in a very simple way. And we'll have 2 omega k. And omega k, as usual, let me maybe put it over here. Omega k is the square root of k dot k plus m squared. What's now nice about this integration measure is that it is Lorentz invariant. Every inertial observer will use that measure. Then we'll have the f of x mu comma k mu, and I would actually like to have a Lorentz invariant oscillator sitting here. I'm going to call the Lorentz invariant oscillator by a Greek letter. We were using a Roman letter A for the oscillator before. Now we'll use alpha. And that's because whenever we use Greek letters, we usually talk about things that are Lorentz invariant. So always the indices of our 4 vectors have been mu's. So I'm writing the alpha there to remind you a Greek letter again. This is going to be a Lorentz invariant oscillator that all inertial observers will agree on what it is. And here we have got G of x mu and k mu, and we'll have an alpha dagger of k. Okay, now what is alpha k? Alpha k is going to be equal to 2 pi cubed, again, just a constant. We'll see where that comes about. We've got 2 omega k, and we've got ak sitting there. And here, the index k labeling the oscillator alpha, you should think about this as a 4 vector, which is omega k followed by spatial vector k. If you like, you are welcome. You are welcome to write alpha with a 3 vector label. Okay, you're welcome to write it like that. It's just notation, just so long as we know we're talking about the same thing. Okay, we'll continue in a moment.